Alright, welcome to another video. In today's video, we're going to be taking a look at a question on chemical equilibrium. We're starting a new series, and this is part one of that series. We're going to be answering a series of exam questions on chemical equilibrium. So in front of me, I've got the 2023 June exam question paper. And we're taking a look at question 6, which is the question on chemical equilibrium. Let's have a read of what it says. So question 6 says you've got 1 mole of pure hydrogen iodide, right? Gas. So we've got 1 mole of that, and we know that it is sealed in a 1 decimeter cubed container at 721 Kelvin. We're told that equilibrium is reached according to the following balance equation. We can see the equation right over there. We've got 2 moles of pure hydrogen iodide decomposes into hydrogen gas and iodine gas. Then we're told that it is found that 0.11 moles of iodine gas are present at equilibrium. So that's the number of moles that is left at equilibrium. And remember, when equilibrium is reached, there is no more change in the concentration of the products of the reactants, because now equilibrium has been established. 6.1 says, was asking us to state the Le Chatelier's principle. Right, so I've gone ahead and written it for us already. So Le Chatelier's principle says that when the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium, and it does this by favoring the reaction. So the reaction can either be the forward reaction or the reverse reaction, by favoring the reaction that opposes that change. So if you increase the concentration of a certain substance, the system will try to decrease the concentration of that substance, and it does that by favoring the reaction, a certain reaction, either the forward reaction or the reverse reaction. Just an example, but that is Le Chatelier's principle. 6.2. In 6.2, we're asked to determine the number of moles of each of the following at equilibrium. So 6.2.1 says the hydrogen gas. So we already know the number of moles of iodine gas at equilibrium. So we're going to use that. 6.2.1. So from the balanced chemical equation, we can see that there is a 1-to-1 relationship between the iodine gas and the hydrogen gas. So if I'm looking for X, which is my number of moles for hydrogen, and I already have my number of moles for iodine, I can just put that there, cross multiply. What essentially I'm doing here is I'm trying to solve for X. And therefore X will be equal to 0.1 moles of hydrogen gas. Okay, this is how you use the stoichiometric ratio to find the number of moles. So you set up your 2 substances, you write down the ratios, you write down your X, which is what you're looking for, you fill in what you know, and then you solve for X, which is what you don't know. All right, and we're going to follow a similar fashion for the number of moles of the hydrogen iodide at equilibrium. So you've got hydrogen iodine, is to iodine. You've got X, that's what you do. So the ratio first is 2 to 1, and X is the number of moles of the hydrogen iodide that you're looking for, and at equilibrium you've got 0.11. That's the number of moles of iodine. So we cross multiply, and then we're left with X being equal to 2 times 0.11, and therefore X is equal to 0.22 moles of iodine. So that's the number of moles of iodine at equilibrium. So hydrogen iodine. at equilibrium. Beautiful. That's done. 6.3 is quite interesting. So we're told that the equilibrium constant Kc at 721 Kelvin is 0.2. And we're told that the temperature is now increased. Okay, temperature is now increased to 850 Kelvin. And as a result of the temperature increase, the equilibrium constant Kc at 850 Kelvin is now 0.8. So the Kc value also increased with the increase in temperature. And the first question is asking us, is the forward reaction exothermic or endothermic? So how do we figure this out? So normally, when you're given an equation, a balanced chemical equation, it's normally written like this. And then you've got a change in enthalpy. And then when it's less than 0, so change in H, that's change in enthalpy. When it's less than 0, that tells you that the forward reaction is exothermic. And if you've got a change in enthalpy that's greater than 0, so a positive number, that tells you that the forward reaction is endothermic. Alright? So that's normally how we tell whether a reaction is endothermic or exothermic, but we're not told about the change in enthalpy in this equation. What are we told about? All we're told is that temperature is increased. Right? So we know that an increase in temperature from Le Chatelier's principle always favors the forward reaction. That we know from Le Chatelier's principle, that increase in temperature always favors the forward reaction. Sorry, not the forward reaction, pardon me. Always favors the endothermic reaction. Pardon me there. Alright, if that's the case, what else do we know? We know that Kc is directly proportional to the concentration of the products. Okay? So what does that mean? That means if Kc increases, the concentration of the products also increase. So in our case, we know that Kc started at 721 Kelvin was the Kc value was 0.02, and then at 850 Kelvin the Kc value increased to 0.09. So it increased. So if the Kc increased, that also means the concentration of the products also increased. So what does that mean as far as the reactions are concerned? Whenever concentration of your products increase, that means the forward reaction is favored. Maybe let's write that down. Whenever the concentration of your products increase, that means the forward, the forward reaction is favored. Alright? So from these two things, because Kc increased, we can definitely tell that the forward reaction was favored. And if temperature was also increased and the forward reaction was favored, therefore the forward reaction has to be endothermic. Alright? So that's how we can tell. So 6.3.1, we can just simply say that the forward reaction is endothermic. 6.3.2 then asks us to fully explain the answer to 6.3.1. So how do we fully explain? So firstly, we say that when temperature is increased, the endothermic reaction is favored. That's our first point. And then we say Kc increased, therefore the concentration of the products also increased, meaning the forward reaction was favored, therefore making the forward reaction endothermic. Alright. So temperature is increased, and an increase in temperature always favors the endothermic reaction. The Kc was also increased as a result of this increase in temperature. So therefore the concentration of the products also increased, and therefore the forward reaction was favored because the concentration of the products increased. Then because the forward reaction was favored as a result of this temperature increase, therefore the forward reaction is endothermic. Beautiful. 6.3.3. Then 6.3.3 is then asking us to calculate the mass of the hydrogen iodide present at the new equilibrium of 850 Kelvin. All right, so now we can't use these values of 0.11 at equilibrium because that's the old equilibrium. Now a new equilibrium has been established with a new Kc, so therefore now we have to set up a new Rice table to figure out what are the number of moles left at equilibrium. Once we have the number of moles left at equilibrium of our hydrogen iodine, we can then use this formula of mass is equal to number of moles times molar mass to figure out the mass of the hydrogen iodide. All right, so where do we start? Let's start with the Kc expression. So the Kc expression will be the concentration of the product. So we've got hydrogen gas multiplied by iodine gas divided by hydrogen iodide squared. And why is it squared? It's squared because you've got 2 moles of the hydrogen iodide. So that's why it's squared. Beautiful. So now we already have the Kc value. We just need to solve for the number of moles of the hydrogen iodide, and we're going to use a Rice table to do that. So you've got R, you've got I, you've got C, you've got E, you've got C again. Then we're going to write the equation here. Just fill in those straight lines. Wonderful. So the ratio, the R stands for ratio. So the R is there, stands for ratio. The I stands for initial. That's the initial number of moles. The C stands for the change in the number of moles. And you must always remember that the change is always related to the ratio. So we use the stoichiometric ratio whenever we're calculating the change. You'll see that in a moment. The E stands for equilibrium. So this is the moles equilibrium. It's the number of moles at equilibrium. And then C stands for concentration. And you remember concentration, that is number of moles divided by volume. So then you've got 2:1:1, that's the ratio. So you've got 2 moles of hydrogen iodine is to 1 mole of hydrogen gas is to 1 mole of iodine gas. Then initial number of moles, remember we're told in the beginning of the question that we have 1 mole of pure hydrogen iodide. So that means we have 1 here. Just write 1. And then initially we're going to have 0 moles of hydrogen gas and 0 moles of iodine gas. The reason for that is at the beginning of every reaction, you have 0 products. Initially, you've got 0 moles of the products, and as time goes by, you're forming the product. So you're going to have 0. And then now this is where we're going to have to use mathematics, right? So we don't know what the change is. So we're going to say, okay, I'm going to set this change equal to X for my iodine, and for my hydrogen, I'm also going to set it equal to X. So whenever you want to use this X method, I always advise that if you've got a molecule or a substance with a ratio of 1, set that equal to X. Okay, set that as the unknown. It just makes the calculations much easier because that way you don't really have any fractions. Okay. So you've got iodine as the change in the iodine as X, and because the stoichiometric ratio is 1:1, so therefore the hydrogen will also be X. And then here you've got the ratio of 1:2, so therefore the change in hydrogen iodine will be 2 times the X. And then we know that products are being formed, so this is a plus, so they're being added, while reactants are being used up, so this is a minus. Okay, so that means at equilibrium we are going to have 1 minus 2x number of moles. That's for the hydrogen iodide. Then for the hydrogen, we're going to have 0 plus x, therefore we're going to have x. And same thing with the iodine, you're going to have 0 plus x, and that's going to give us x. And then we're told that the volume is equal to 1 decimeter cubed in the question. So whenever we're trying to calculate the concentration, we're just going to divide that by the volume of 1. So then we're going to have 1 minus 2x over 1. So that's going to give you 1 minus 2x. You've got x over 1. That's going to give you x. You've got x over 1. That's going to give you x. And this represents the concentrations at equilibrium. Now that we have the concentrations at equilibrium, we can substitute them into our Kc expression. So let's just rewrite the Kc expression here. We've got Kc is equals to the concentration of hydrogen gas multiplied by concentration of iodine gas divided by the concentration of hydrogen iodine. Then our Kc, remember we're looking at the Kc at 850 Kelvin, and we know that the Kc value is 0.09. So we're going to substitute there. 0.09 is equal to concentration of hydrogen gas. It's going to be X multiplied by the concentration of iodine gas. That's X divided by the concentration. Remember, sorry, this is squared. The concentration of hydrogen iodine is 1 minus 2x squared. And then now we can solve for x. So if we cross multiply, we're going to get 0 times 0.9 multiplied by 1 minus 2x, 1 minus 2x. So that's us cross multiplying there. And then we're going to get x squared on the right hand side. If we keep this 0.0 and then you expand this brackets, we're going to be left with 1 minus 4x minus 4x squared is equal to x squared. If we continue, then we're going to have 0.09 is equal to negative 0.36x minus 0.36x squared minus x is equal, minus x squared is equal to 0. Then you're going to have negative 0.64 x squared minus 0.36 x just remove this minus, this equal sign. It's just supposed to be 0.09 here. Then plus 0.09, all of this is then equal to 0. At this stage, you are allowed to use the quadratic formula to try and solve this. Divided by 2a. So this will be your a value, this will be your b value, this will be your c value. All right, that is a, this is b, this is c. Okay. All right. And then I can leave that to you to substitute, but you get two answers. The first answer you get is that x will be 0.18. I had it here. 1875. That's with the positive x. And the negative x will be negative 0.75. So now obviously x can't be negative because you can't have a negative number of moles. So therefore the x value is actually equals to 0.1875. So remember that represents number of moles. Remember we are actually looking for the number of moles of the hydrogen iodide at equilibrium. Okay, and that is this section over here. So it's 1 minus 2x, because remember this is equilibrium and that's the number of moles of hydrogen iodide at equilibrium. So this is equal to 1 minus 2x. When we substitute, we get 1 minus 2 times 0.1875. Therefore, the number of moles is equal to 0.6. 0.625 moles. Okay, so that's the number of moles of the hydrogen iodide at equilibrium. So now that I have the number of moles, I can now use this formula to calculate the mass, because that's what I'm really looking for, the mass of the hydrogen iodide that is left at equilibrium. Mass is equals to number of moles multiplied by the molar volume. So the molar volume of hydrogen iodide, we can use the periodic table. So the molar volume of hydrogen is 1, plus the molar volume of iodide is 127. So therefore, the molecular volume together of hydrogen iodide is 128 grams per mole. When you substitute, we have 0.625 multiplied by 128 grams per mole. And then you're left with 80 grams. And that is the mass of the hydrogen iodide that is left at equilibrium. Wonderful. I will add these notes as well at the bottom. You can find them at the bottom in the description of the video. So you can download them and take a look at them on your own. But that's how you solve this question. So I hope you found this insightful. We will be having a part 2 where we're going to be answering a different question on chemical equilibrium. So stay tuned for that. In the meantime, please do hit the notification bell, subscribe if you haven't subscribed, and I'll see you in the next one. Thank you so much.